Hello, welcome to tutorial number 10 of the linear algebra course at AOU. This tutorial number 10 is related to section 3.2 titled subspaces. Let's start off by looking at some definitions. Let V be a vector space and W be a non-empty subset of V. In other words, W is a set that at least has one vector in it, and at the same time W is included in the vector space V. If W is considered a vector space with respect to the operations in V, then W is called a subspace of V. In other words, in order for W to be a subspace of V, it must inherit all the rules and properties that we talked about before in section 3.1. It must respect all these properties in order for it to become a subspace of V. Example, W1, the set W1 that includes the vector XX, where X belongs to R, is a subspace of the vector space R2, as we will see later. Also, the set W2, which is the vector XY 0, where X and Y belong to R, is also a subspace of R3. Let's look at the correct rules for determining whether a particular set is a subspace or not. Theorem here defines these rules. Let V be vector space with operations plus addition and multiplication, and let W be a non-empty subset of V. So the first condition is that W is non-empty. The set W is a subspace of V if and only if the following two conditions are met. One, any two vectors in W, if we add them up, the output or the outcome of the addition must be in W. In other words, the form of the outcome must meet the same form as any vector that is already included in W. The second condition is that if we take a vector, any vector in U, and we multiply it by a real number, the outcome of this product is again a vector in W, which means that the outcome must have the same form as any vector that is already in W. If these two conditions, along with the set being non-empty, are met, then W is considered to be a subspace. Otherwise, if any one of these conditions is violated or is not met, then W is not a subspace. Let's look at some examples. Example that we saw before in the previous slide, W equal to XX, where X belongs to R, is a subspace of the vector space R2. This is the proof here. First of all, the vector 0, 0 belongs to W. Since X belongs to R, it can take the value of 0. Therefore, W is non-empty. The second condition is that U, if we take two vectors, U and V, as such, and they both belong to W, if we add them up, we get X plus X prime, X plus X prime, and it is clear that this will generate two real numbers that have the same form as the original vector here. That means that the outcome here of this addition is a vector that belongs to W. Likewise, if we take the vector U and we'll multiply it by any real number, we will obtain Rx, Rx, and it is clear that it has the same form as this, and therefore this product belongs to W. Since all these three are met, therefore the vector or the set W is a subspace of V. Let's look at more examples. Example 2 here. Show that W, which is made up of the vectors A, B, C, where A, B, and C belong to R, and in particular C is equal to the addition of A plus B. Let's show that this particular set is a subspace of the vector space R3. In order to prove that, we will apply the definition or the theorem that we saw previously. Here, since A, B, and C belong to R, then we can write that W is equal to A, B, and we substitute C by its own value, which is A plus B. Therefore, here 0 is clearly a point or a vector that belongs to W. Therefore, W is non-empty. Also, if we take two vectors that have the same form, exactly the same form as the vectors here, any vector in W, but in particular U and V, and we add them up, we obtain this outcome here. It is clear that this outcome belongs to W since it has the same form as the original one here. Also, if we take any vector U or V and that belongs to W and multiply it by a real number, we obtain the output here RA, RB, RA plus RB, which also belong to W since it has the same form as this one. All these three indicators show that this subset W is a subspace of the vector space R3. Another example here show that W equal to AB, A plus B plus 1 is not a subspace of the vector space R3. Again, we will revert to the theorem. If we looked at the vector 0 to see if it's empty or not, it is clear here that 0, the vector 0 does not belong to W, since if the values if A and B take the value of 0, we will have 0, 0, and 1, which is different than the 0, 0, 0. Therefore, 0 is not does not belong to W, and W is not a subspace of the vector space R3. It is sufficient to prove that. However, to show that the other conditions as well are not met, we will continue with this to show that the second condition as well is not met. If U is equal to AB, A plus B plus 1, and V is equal to A prime, B prime, A prime plus B prime plus 1, if we add these two together, we obtain A plus A prime, B plus B prime, A plus A prime, B plus B prime plus 2. It is clear here that from this last element here, that this is different than this one here, does not conform to the same rule or form as the original one, because the plus 2 is different than the plus 1 here. Therefore, again, this shows that W is not a subspace of the vector space R3. It is sufficient to show that any one of the three stated rules in the theorem are not met, any one of them, to conclude that the set is not a subspace of the vector space. Another example here, which is the last one, I believe. If X is the vector 1, 2, 3, and Y is another vector 4, 5, 6, both they belong to R3, show that W, which is made up of AX plus BY, where A and B belong to R, is a subspace of the vector space R3. Again, let's apply the rules of the theorem. 0 here is clear that 0 belong to W, since A and B can take the value of 0 since they belong to R, and any vector multiplied by 0 will produce a value of 0. Therefore, W is non-empty. For every vector U, condition number 2, that is equal to AX plus BY, and V A prime X plus B prime Y, that both belong to W, if we add them up together, we obtain AX plus BY plus A prime X plus B prime Y. If we factor the X and Y vectors, we obtain A plus A prime times X plus B prime times Y. It is clear that this belongs to W, since it has the same form as this, because A plus A prime is a real number that is equivalent to A, and B plus B prime is another real number that is equivalent to B. So it has the same form as the W here. Lastly, for every U equal to X plus BY that belongs to W and any real number, if we multiply the real number times the vector U, we obtain RA times X plus RB times Y. It is clear here that RA is similar to the A here, and RB is similar to the B here. They are all real numbers, and they conform to the same form, exactly the same form here, therefore it belongs to W. Thus all these three conditions show that the set W is a subspace of the vector space R3. This concludes section 3.2 and tutorial number 10, and thank you very much.